We've been introduced to the idea of exponential functions, but e to the x isn't the only base that we have. You might think of like 2 to the x or 1/2 to the x. So for instance, in like half-life models, what you can do is set up something like 1/2 to the t, so you can determine how much time it takes for an item to be have half as many as it has before. So you figure out how much time it's half and half and half. So that's like 1/2 to the t. But you can have any kind of base. You could have 2 to the x or 2 to the t. You could have 3 to the x. You could have 1.5 to the x. You could have pi to the x. So we want to talk about a meaningful way to discuss all of these different bases. And to do that, we're going to review some information that we've already covered. The first one is this inverse identity that says e to the natural log of x is equal to x. And we know this because these are inverse functions. E and the natural log or e to the power and the natural log of something are inverse functions, so they sort of undo each other. And the second thing is that e to a power to another power is just e to those powers multiplied. And that's properties of exponents. That's not anything extra special. But we're going to use these two properties to develop an idea about arbitrary bases. So in the first case, if instead of using x here, I use just some number a, and for our purposes, we're going to say that a is not equal to 1, because that would cause some issues here. Actually, in this case, a being 1's okay, but anyway, but we're going to use positive numbers of a because the natural log takes positive numbers. So e to the natural log of a is equal to a. And then secondly, if I have e to the natural log of a times x, then by this property, since they're multiplied together, I can rewrite that as e to the natural log of a to the x. So I'm just using algebraic properties to represent this quantity. But by property 1, this term is just a. So this is really a to the x. So we can follow that down here to say that e to the natural log of a times x is equal to a to the x. And why do we want to do that? We want to do that, we want to represent a to the x, we want to rewrite it like this because this format is very convenient for performing calculations with calculus. So to sort of reiterate, for any positive number a, where a is not equal to 1, a to the x is e to the natural log of a times x. Now, this kind of works when a is equal to 1, but it's not very useful because it's 1 to the x is e to the 0 times x, and then so that's kind of like 1 to the x, but there's some issues there if you do it like that. So for practical purposes, we're just going to consider the case where a is not 1, but is generally positive. So the reason we want to write this as that is because, and we'll come back to this in a second, if you remember from our study of the derivative of the natural number, or the natural exponential function, e to some number times x is that number times e to some number times x, right? That's a consequence of the chain rule. E to the something, the derivative of e to the something is e to the something times its derivative. And specifically when you have that something being natural log of a, then we could say, all right, well, the derivative of a to the x is the derivative of e to the natural log of a times x, which matches that structure. So then we bring that constant out front when you take the derivative, and then we leave this e to the natural log a times x alone, and we can rewrite that as natural log of a times a to the x. I know that's a lot of words there, but realistically the big thing is that the derivative of a to the x is just the natural log of a times a to the x. So what you're seeing is if that base a was not a, it was actually e, for instance, then this would be natural log of e, which is just 1, and that will be e to the x, which is what we expect. And then of course we have some properties, and these are just general exponential properties, that a to the 0 is 1, a to the x times a to the y is a to the x, that should be x plus y. I apologize, that should be x plus y. A to the x divided by a to the y is a to the x minus y, and a to the x to the y. Now there is a to the x times y. So I apologize there. Now, this is kind of the rules for this. I'm going to skip down to here and talk a little bit about the antiderivative for a moment. So we see that the derivative of a to the x is this. So notice that the derivative is, the only difference is that constant. So if we're doing an antiderivative, instead of multiplying a natural log of a, we divide a natural log of a. So it's sort of like an inverse operation. And then of course don't forget your arbitrary constant. Don't forget your arbitrary constant. And they follow, and then following on these inverse properties, we have some stuff from the natural log here. I was going to cover that. Let me come back to that in a second. So we've covered the idea of an arbitrary base for an exponential function of a to the x. But what about for the natural log? The log of any base. So we know a little bit about the natural log, and that's log base e. And you might have seen things like log base 10. That's a pretty common one that gets used in applications. But what about logs of arbitrary bases? These are really useful when the system you're dealing in is, again, some sort of arbitrary base. Like base 2 is a very common number system when dealing with computing theory, because it's a binary computer. And base 3 is actually used often for these rotation and permutation groups. Some of this kind of advanced mathematics, but the whole point is that you can use these arbitrary bases. You don't have to use base e, you don't have to use base 10. So you might ask yourself, okay, I know that the derivative of the natural log is 1 over x, but what's the derivative of an arbitrary log, like log base 2 of x, for instance? Well, what we find is that the derivative of an arbitrary base is 1 over natural log of that base times the natural log of x. Sorry, not the derivative. The definition of this log is this. I apologize, I'm kind of all over the place here. The definition of this is log 1 over natural log of the base times natural log of x. Now another way that you'll see this written sometimes is natural log of x divided by natural log of a. That's another way to write that. That's a very common way to write that. It's called the change of base formula. One of the reasons we don't like to write it like this is because we're about to apply some calculus to this, and we know the derivative of this is 1 over x, and we know that this is just some number, it's a constant. So the derivative of an arbitrary base is 1 over the natural log of that base times 1 over x. So all that tells us is that if we're dealing in these arbitrary bases, we really just have to perform this change of base formula, and everything comes out clean. That's really nice. Now, the logs of arbitrary bases basically have the same properties that the natural log does. The log of 1 is 0. If the base and the argument match, it's equal to 1. If you have a product here, you can separate that into 2 logs added together. If you have a quotient here, you can represent that as 2 logs being subtracted. And if you have a power rule, you can bring that power out to the front. So these are all properties that we're well aware of. And the way that they're all related to the arbitrary base exponential function is that if you have y equals a to the x, you can rewrite that as x is log of an arbitrary base of y. So sometimes that's useful because this may be kind of nice, but if you write it like this, it's a lot. Maybe it's cleaner. Maybe you know how to simplify it in a specific way. Really, this is just a natural consequence of taking the log base a of both sides. If you take the log base a of this side, you get that term. If you take the log base a of this side, you get like this. Well, you really get like these two combined together that simplify to x. The next thing is the inverse property, that a to a power and log base a of a number, those are inverse functions. So just like this right here, the same inverse property applies. Again, now they have to be careful. This is only true for positive values of x because it's being fed through the log first. So you're restricted by the domain of the log. However, if you sort of have the inverse or starting point, you have log base a of a to the x, you can actually feed in any x, and that's because it gets run through the exponential function, which has a domain of all real numbers, and then will generate a value that's valid for the log every time. So this relationship is easy to deal with. This one you have to be a little more careful with. But generally speaking, these are the properties of logs. I know it's a lot. There's a lot written up here, and it's not well organized. I apologize for that. But we're going to do some examples involving these arbitrary bases and logs with arbitrary bases and do a little calculus. And what you're going to find is it's actually pretty straightforward.